Hello everyone, my name is Uma Patricia and today I will be presenting the introduction of gravimetric analysis. This is actually one of the oldest and most accurate quantitative analytical methods. What makes it incredibly unique is that it does not require calibration against external standards. Instead, it determines the amount of an analyte purely through measurement of mass. Because of how reliable it is, it's widely used across analytical and environmental chemistry today. So, what is the core principle here? Essentially, gravimetric analysis is based on determining the quantity of an analyte through precise mass measurement. We take the analyte present in a solution and chemically convert it into a stable and insoluble precipitate with a known chemical composition. Once that precipitate is formed, we follow a 4-step process. The first step is isolated through filtration. Second, it's washed to remove any impurities. Third, it is tried to completely eliminate moisture. And fourth, it's accurately weighed using an analytical balance. Let's look at a real-world application of this principle, water quality control. Our objective here is to determine the concentration of chloride ion in a water sample through the formation and measurement of a silver chloride precipitate. This helps us evaluate water quality based on the chloride contamination level. As you can see in the workflow chart, the process is straightforward, starting with our water sample, then we add silver nitrate to the sample. This forms our precipitate. We then filter and wash it, followed by drying and weighing, which allows us to calculate the final chloride ion content. Moving on, let's look at the chemical reaction taking place. Silver ion plus chloride ion react to form solid silver chloride. This specific reaction is ideal for our analysis because it forms warped precipitate. Has low solubility, meaning the solid won't easily dissolve back into the solution, and ultimately ensure high analytical accuracy. And with that, I will hand it to the next person.
Hi, my name is Nur Shafini Nadia binti Muhammad Nazri. For the next part, let's look at the theoretical framework. Let's dive into the core chemical mechanism behind our analysis, which relies on the precipitate of silver chloride. When a solution of sodium chloride is added directly to a solution of silver nitrate, an instant reaction occurs. This reaction generates an insoluble crystalline silver chloride precipitate, as you can see from the chemical equation below. The silver ions combine with the chloride ions to form a solid precipitate, leaving sodium nitrate in the solution. This instantaneous reaction is crucial because it forms an absolute stoichiometric link between the mass of the weak product and the exact concentration of our target analysis. Now, why exactly do we use silver chloride for this gravimetric analysis? There are 5 key properties that make silver chloride ideal for this method. First, it has incredibly low solubility. With a low solubility product constant of 1.8 times 10 to the power of -10, it is heavily sparingly soluble in water, it ensuring that virtually all the chloride is precipitated out without loss. Second, it offers a stable chemical composition. Silver chloride is stable in air and does not decompose when we dry it in the oven. Third, it easily filtered and dried. It forms a distinct white crystalline precipitate that collects efficiently without clogging or passing through the filter. Fourth, it has a known fixed chemical formula. This trick is 1-to-1 stoichiometry between silver and chloride ion allow for highly accurate, predictable calculation. Finally, these combined traits make it ideal for gravimetric analysis, ensuring our final analytical results are both highly accurate and reproducible.
Moving on to the methodology, our laboratory procedure requires meticulous execution to prevent any sample loss. We begin with step 1, sample preparation and acidification. First, we measure a precise volume of water sample into a beaker and add a small amount of nitric acid. This acidification step is crucial because it prevents interference from other ions like carbonate or phosphate, which would otherwise form competing insoluble silver salts. Next is step 2, preparation and digestion. Here, we slowly add a slight excess of silver nitrate solution under constant stirring to ensure all chloride ions react completely. We then heat the mixture just below boiling for 45 to 60 minutes for digestion. During this process, you will observe the cloudy solution coalesce into large, heavy particles of silver chloride, leaving a clear supernatant liquid above them. Step 3 is filtration and washing. After allowing the mixture to cool, we filter the precipitate using pre-weighed horizontal glass crucible or a punch and funnel setup that connected to a vacuum flask. Here is the standard laboratory configuration used to isolate the solid analyte during this stage. We then wash the precipitate with a very dilute nitric acid solution to safely remove excess silver and nitrate ions without dissolving the silver chloride. Finally, we have step 4, drying and constant weight. We place the crucible with the precipitate into an analytical drying oven at 110 degrees Celsius to 120 degrees Celsius for 2 hours to drive off all the moisture. After cooling the crucible in a desiccator, we weight it. We repeat this heating, cooling, and weaving cycle until the mass stabilizes to within 0.3 milligrams, successfully achieving the constant mass. That concludes the 4-step methodology for isolating the solid analyte. I will now pass the presentation over to our next teammates for the next section.
Hi, Assalamualaikum. My name is Hairunisa Shafika. Now, let's move on to the result and calculation. As for the result here, is mass of empty glass crucible obtained is 24.3215 gram. And as for the mass of crucible plus dried of silver chloride precipitate is 24.6083 gram. Therefore, the net mass of collected silver chloride precipitate is 0.2868 gram. Now, let's move on to the calculation part, which is we have to determine the analyte and precipitate first. As for the analyte is chlorine ion and precipitate is silver chloride. Now, we can determine the value of formula weight. Formula weight for chlorine ion is 35.5 gram per mole, and as for the formula weight for silver chloride is 143.5 gram per mole. Now, we can determine the gravimetric factor. As for the formula state here, we can conclude that we have calculated the gravimetric factor is equal to 0.2474. Now we can move on to calculate the mass of chlorine, which the mass of silver chloride we have weighed earlier is 0.2868 gram. Therefore, the mass of chlorine we can determine by mass of silver chloride times with the gravimetric factor. Therefore, the mass of chlorine ion is 0.0710 gram. Now, we can determine the concentration. How to determine the concentration? So, sample of volume is 100 mm or equal to 0.1 liter. Therefore, we have to convert the mass of chlorine ion into milligram, which is we obtain here is 71 milligram. Therefore, the concentration of chlorine is 71 milligram divide by 0.1 liter. Therefore, the final calculated here concentration of chlorine is 710 milligram per liter or ppm.
So to wrap things up, there is only one thing when it comes to analytical balance that you can always count for, which is mass. So, did we achieve our objective? Yes, absolutely. By applying classical gravimetric analysis, we successfully determined the exact concentration of chloride ion in our water sample. We use precipitation gravimetry, which simply means we added a specific reagent called a precipitant to our liquid sample. This triggered a chemical reaction that took our dissolved analyte and transformed it into a solid insoluble compound. Specifically, we use silver nitrate to convert those dissolved ions into solid silver chloride. By weighing the final solid product, we got the precise data that we needed.
Now let's talk about what makes gravimetric analysis so powerful. At its core, gravimetric analysis is an incredibly accurate and precise method. It relies entirely on a sample's weight to calculate exactly how much of the material is present. Because it measures mass directly, it leaves virtually no room for machine error and completely skips the need for calibration standards. When done carefully, it is so precise that it has been used to calculate atomic masses down to 6 decimal places. However, there is some limitation to this method. First, it has limited scopes per analysis, meaning you cannot simultaneously multi-component testing. Second, the procedure itself is highly convoluted and sensitive, and it demands a high level of skills, and there is always a lingering risk of procedural failure if you aren't meticulous or careful. Well, despite these challenges, it remains a highly valuable and a foundation tool in analytic chemistry.